Welcome back to my today's session of network analysis. Today I am going to tell about the resonance for the parallel AC circuits. In my previous lecture, we have discussed about the series AC circuits resonance, and today we will emphasize on the different type of parallel AC circuits. Myself, Dr. Sayanti Chatterjee, Associate Professor of Electrical and Electronics Engineering Department of IARE, Hyderabad. So first, what is the course objective? There are different course objective of this subject, and here we are going to specify the necessary mathematical background for the transient analysis of DC and AC circuits. We will give the emphasis on the AC circuits and the study the differential equations like this. And we are also, what is the course outcome? What is the outcome? Discuss the steady state response and resonance for electrical circuits to AC supply. So we will now, today's lecture is based on the resonance of the electrical circuits, and we are confine our main work on the parallel circuits. So let's start today's topic. So first we will discuss before that the RLC circuit series. We have given plus 2 or 3 lectures on the RLC series circuit. Just before starting, I will want to give a small recap of the RLC series circuit. What is RLC series circuit? So we are connecting our AC source and R, L, C all are connected in series. So this is the series connection, and here we are showing some parallel connection where R, L and C are in parallel. So this is the series circuit and this is the parallel circuit. So this is our R, L and C. The basic difference between an RLC circuit series is the current is constant throughout the series circuit. In the RLC series circuit, current is constant throughout the circuit, and contrary to that or unlike that, in the RLC parallel circuit, the voltage is constant in each branch. The voltage is constant in the each branch. And there we got, in the previous lecture we have discussed in details, just on quick review, that Z is equal to, we got R square plus XL minus XC square. What is R? R is the resistance. What is XL? We got 2 pi FL. And what is XC? XC we got 1 by 2 pi FC. We call it omega L, and this is, we call it omega C. So this is called the impedance. This is called the impedance. This is the inductance, and this is called the capacitance, and both together called X. And what is the meaning of X? X is called the reactance. So X term is known as the reactance of the circuit. In the resistance, the power is dissipative, and in the reactance, the power energy is stored. Now we are doing the same thing for an RLC parallel circuit. You can find here the current is fixed, current is changing, and the voltage is fixed in the each branch. So each branch we can think the voltage is Vs. This point Vs, this point Vs, and this point Vs, and all are in the ground potential. You can see all the voltage is in ground potential, means this is in the 0 volt. So we can use here KCL, Kirchhoff's current law. Here we are doing everything using the KVL, but here we are doing everything in the Kirchhoff's current law. What is Kirchhoff's current law? Tells that the current coming to any junction is equals to sum of the current going from that node. What is the KCL is telling? Current entering in a junction is equal to the summation of the current coming out from that node or junction. So here current I is coming. I am writing here the I, as I told in the series resonance many times, that the when we are dealing with the AC, the addition is not normal scalar addition. The addition always means the addition is the vector addition, as it has a magnitude as well as the direction. So what is I? I is equal to IR plus IL plus IC. So we can write it I is equal to IR plus IL plus IC. Now what is I? I, we know I is equal to V by Z. So here VS minus 0 by Z. What is IR? VS minus 0 by R. And what is IL? IL is VS minus 0 by XL plus VS minus 0 by XC. So what is the, everywhere we can find that VS is constant. So what is the meaning of this? So we, as this and the what I will tell, these are the vector sum, we cannot do the mathematical addition normally. What we can write that VS by Z, or we can simply write it VS by R plus here VS 1 by XL minus 1 by XC. So this is the basic things we are getting. So what is the R? R is known as the, what is 1 by R? 1 by R is basically known as the, 1 by R is known as the conductance. We have already discussed about this, that the 1 by R is known as the conductance, and the unit of conductance is mho, or we can write it ohm inverse. What is the meaning of the conductance? The property of any material to oppose, allow to flow the current. So G is equal to 1 by R. What is 1 by Z? Here in this side we are getting VS by Z. So what is 1 by Z? 1 by Z we are writing as 1 by Z we are writing as Y. Y is known as the admittance. Y is known as the admittance of the circuit is equal to 1 by Z is equal to square root of G square plus B square. What is the conductance? Conductance G is equal to 1 by R. 1 by XL. 1 by XL is known as the inductive susceptance. What is the 1 by L means? 1 by XL means inductive susceptance is equal to 1 by 2 pi FL. So BL is equal to, actually what is BL? BL is equal to 1 by XL. And what is BC? BC is known as the capacitive susceptance. So we are getting here 1 by omega C. So we are getting here 2 pi FC. So all the units of BL, G, Y, all the units are in mho or ohm inverse. So as we are writing XL and XC together as X, here BL and BC both are written here by B, and the equation has been changed by, this is only the magnitude. We are not talking about the direction. If we take only the magnitude, Y is equal to square root of G square by B square, where G is equal to 1 by R and B is a part of the BL and BC. So this is the basics of an RLC parallel circuit. Next, so how we can calculate? We told it is a vector sum. So while we are getting on vector sum, to solve this we have to draw the phasor diagram. So already here you can see that this is the phasor diagram, but before drawing this I will discuss it, that as in the RLC circuit current is constant, we are taking current as the base. Similarly in the RLC parallel circuit, voltage is the constant, so we will take voltage as the base or voltage as the reference. Which voltage? Vs. Now what is the current? we know current through the resistor is always in phase with voltage. Current in the resistor is always in phase with the voltage. So here we are getting the Vs. So this is the current IR, the current through the resistance. Now again we are remind the civil rule. In the capacitor, I leads B. So current through the VC will be always leading. The IC will always leading, and IL will always lag the voltage. So this is our basic circuit. Now again, if IL is greater, there are two cases. So if generally IL is greater than IC, so if this is the IL minus IC, so this is our supply current, because we know IS is equal to IR plus IL plus IC. So as it is in summation, so we can write that now what will happen if, and this is the theta angle. What is the theta angle? Theta or phi means the angle in the, this is the power factor angle. Angle between voltage and current is known as the power factor angle. So this is the case when IL is greater than IC. Now what is resonance? We know resonance means the condition of any circuit when XL is equal to XC. Means the voltage across the voltage drop of XL is equal to XC. So parallel resonance occurs when the supply frequency creates the zero phase difference between the supply voltage and current, producing a resistive circuit. As in the previous slide, we checked that the IS, the total current, and the VS, the total supply voltage, has an angle theta. So this is called the phase angle. So what is the meaning of the resonance? Parallel resonance occurs when the supply frequency creates zero phase difference between the supply voltage and current, producing a resistive circuit. Resonance occurs in a parallel RLC circuit when the total circuit current is in phase with the supply voltage. So we can tell it like that: when the parallel RLC circuit, when the total current is in phase, means the angle is 0 degree with the supply voltage as two reactive components. This is the one important line. When the two reactive components means XL and XC cancels each other. When they cancels each other, we can tell the system is in the resonance condition. At the resonance, the admittance of the circuit is minimum and equal to the conductance of the circuit. As we know that at this condition, the admittance of the circuit will be minimum and equal to the conductance of the circuit. So this is the meaning of the resonance. So XL is equal to XC. So what are the properties? A parallel RC circuit at resonance condition, the admittance is minimum and equal to conductance. So what we got? We got in the circuit Y is equal to, what is the Y? Y means admittance is equal to what we got? G square plus B square. G is equal to conductance and B is equal to the susceptance of the circuit. So what is current I? What is current I? We know current is equal to V into Y. Actually V by Z. 1 by Z is equal to Y. V by Z, as 1 by Z is equal to Y, we can write V into Y. Now, when as per the definition of the resonance, B has two part. One is BL And another part is BC according to the definition, when BL is equal to BC. So what is the meaning of BL? BL means the inductive susceptance is equal to the capacitive susceptance. So BL is equal to BC. So what will happen? What is B? B is nothing but the 1 by XL by 1 by XC. So BL minus BC. So if BL minus BC is equal to 0, so what is Y? Y is equal to only G. Y is equal to G. So as there is no addition term, we can tell that the admittance is minimum. The admittance is minimum and the conductance, and it equals to conductance. And what is current? If Y is less, then I should be less. So current will be the minimum value. Next point. Below the resonant frequency, the circuit behaves like the inductive circuit, and above the resonant frequency, the circuit behaves of the capacitive circuit. We will discuss this point later with the graph. And at the resonance, the magnitude of the current through the inductance and capacitance will be Q times in the current supplied by the source, but they are in the phase opposition. So Q times means it depends on the Q factor of the circuit. It depends on the Q factor of the circuit. Next, we are discussing about what is the resonance frequency. What is very, very important. So as we discussed before, XL is equal to, this is for the series circuit, we got XL is equal to XC is equal to 2 pi FL is equal to 1 by 2 pi FC. This is we are getting from the series circuit. If we are moving to the parallel circuit, what will happen? We got BL is equal to BC. So the inductive susceptance is equal to the capacitive susceptance. What is inductive susceptance? 1 by XL. 1 by XL means 1 by 2 pi FL is equal to 2 pi FC. So again similarly we are getting F square is equal to 1 by 4 pi square LC. For the both case we are getting the same equation. So F is equal to root of 1 by 4 pi square LC and FC is equal to 1 by 2 pi root of LC. We can tell it is the resonant frequency. So what is omega R? 1 by, this is in the hertz and this is in the radian. This is in the hertz and this is in the radian. Omega R is equal to 1 by root of LC. So what is the case of the impedance? We told before also that what happened in the circuit. Now we will discuss this with the curve. So if we increase the frequency, what will happen? It will increase, the impedance will increase, and we know if we are thinking about the impedance, this is for the impedance only, but at the FR point, the Z is maximum. What is the meaning of the Z is maximum? Z is maximum means if we draw the Y, Y is minimum. So actually we cannot plot the Y, rather we are plotting the Z. So what will happening in the parallel circuits, impedance is at its maximum at the resonance. Actually in the parallel circuits, admittance is minimum. Admittance is minimum, we can tell it as the impedance as its maximum at the resonance. Unlike the series resonance circuit, the resistor in a parallel resonance circuit has a damping effects on the circuit's bandwidth, make the circuit less selective. What is the meaning of the less selective? Actually, if we check this circuits, what is happening? This is the F. F means the maximum frequency. So in this side, what is happening? Xc, the capacitive reactance is much more greater than the XL, and here XL is greater than the Xc. So this is the two sides. So it is an inductive circuit, and this is waves like a capacitive circuit. Resistance doesn't depend on the frequency. But if the case the resistance is very small, what will happen? The Z will be the very small value. As a result, the current will get in the peak. So this is called the higher selection or more selectivity. But when the resistance have some damping effect on the circuit's bandwidth, making the circuit less selective. Less selective means that it should be picky, but sometimes due to resistance value, it is not become so much picky, it becomes flat-headed. So this condition is telling that the circuit becomes the less selective. Next, also since the circuit current is constant for any value of impedance, the voltage across the parallel resonance circuit will have the same shape. If we are not, the shape is always like this. The magnitude may change, but the shape will be always like this. Now we are going for another case study where we have taken the practical condition. In the practical condition, inductor cannot stay without the resistance. So what is happening? R and L is always in the series circuit, and capacitor is always in the parallel with the resistance. So this is a combination of a RLC parallel circuit where R and L are in series and capacitor is in parallel. So what will happen in this case? First we have to draw the circuit. So here you can see there are two current we have written by IL and IC. IL and IC. Correct. So this is so what is I? I is equal to actually IL plus IC current. IL plus IC current. Now we are giving the voltage V here. We are giving the voltage V here. And we know the current through the resistance is always in phase current is always in phase, and IC is always the 90 degree to the voltage. So first we are drawing first we have drawn the IC. Can you see? This is first we have drawn the IC, which is 90 degree apart with the voltage, which is 90 degree apart of the voltage. Now we are coming to this current. So this is basically the IR current. If we draw only this portion, say this voltage drop is V. I am just drawing here. We have a voltage drop V. So what is happening here? This is the voltage drop V. What is the current here? The current is I into R. I into R. So we are taking I as the base, and what is V? V is equal to I into R. What is VL? What is VL? VL is always the 90 degree apart. VL is always 90 degree apart. So we can think that the VL and the IL current is, we can think is, if this is that angle, then what is the voltage? Voltage is this angle. So we can think that the current is always if this is the theta angle, the cos theta angle is similar to the IR current. Correct? That the VL cos theta is parallel to the same, and this is the IR sin theta. We are doing that work only. So IL cos theta and this is our IL sin theta. If the angle is theta L, IL cos theta L, and this is IL sin theta L, and this is our IL current. Clear? I think it is clear now. Or I can make it more clear that IC current and IL current will be 90 degree apart. So this is the theta L, IL, and IL cos theta L, IL sin theta L. So what is the IC and IL theta L? Both are in the 180 degree apart. So IL IC sin theta L is equal to IC. Both are opposite direction. So what is IL? IL is equal to V by Z. What is IL? V by Z. So what is Z? Z is equal to nothing but here R plus XL. What is sin theta L? Sin theta L means the angle, and it is XL by Z. You can see from here, if this is our theta L angle, so sin theta L is equal to XL by Z. What is IC? IC is equal to, as per the drawing, V by XC. So we got this equation. So if we are calculating this equation, what we are getting? IC is equal to IL sin theta L, and IL is equal to, what is IL? V by Z sin. So what is sin theta L? Sin theta L is equal to XL by Z. Up to this is we got. So IC means V by XC, IL means V by Z, sin theta L means XL by Z. So we write the equation. This is our IL. What is this? This is our sin theta L. So what we got here? V by XC is equal to, so we can cancel out V from the each side. So what is the next thing we got? XL into XC is equal to Z square. If we cancel the V from the each side, we are getting XL into XC is equal to Z square. So what is that? XL. XL means we know omega L, XC means 1 by omega C. So omega LC is equal to Z square. So L by C is equal to Z square, and then what is Z? Z is equal to square root of L by C. This is the another relation of the impedance, another relation of the impedance of a series parallel circuit, which is the more practical case. So we can write again, we got L by C is equal to Z square. So what is the meaning of Z square? Here Z is the impedance. Here what is the Z? Z is equal to, we can see, R square plus L square. What is Z square? R square plus XL square. We are using this value here. So L by C is equal to R square plus XL square. So L by C is equal to R square 2 pi F naught L square, because we are thinking about what is F naught. F naught is nothing but the resonant frequency. We are calculating it for the resonant frequency. So 2 pi F naught is equal to, so 2 pi F naught L square is equal to practically L by C minus R square. So if we put the value, we are getting F naught is equal to 1 by 2 pi square root of 1 by LC by R square by L square. In the practical case, this is the resonant frequency for an resistive circuit. So this is the basic thing. So I will go for a quick recap of this topic, because this is very, very important. So we are taking one RLC basic circuit where it is an IC, this is an IL, R and L is in parallel circuit. So first we have to draw the we have to draw the circuit. We are taking V as the V in the basic circuit. This is the V voltage. So what is the voltage drop between this portion? We have to take this. We have to draw first this. So how much current is flowing? The voltage is V also, as this is the parallel circuit. The voltage drop is V and the total current is IL. Now IL is the current, and what is IR? IR is the same phase with the V. IR should be same phase with the V. So what will happen to the IL? IL will be the 90 degree apart, and we are dividing it in the two parts. One is IL cos phi L and one is the IL sin phi L, and total current is IL. IL cos phi L is equals to the R, and IL sin phi L is equal to the IC. So again, what we are doing here? We are just writing what is IL sin phi L is equal to IC. So IL is equal to V by Z, sin theta L is equal to XL by Z, and we are just substituting the value. If we are substituting the value, we are getting the equation XL XC is equal to Z square, Z is equal to square root of L by C. And from there we got F naught is equal to 1 by 2 by root of 1 by LC minus R square by L square. Now what will happen if it is a pure inductive circuit? Because pure inductive circuit is not possible in the practical case, but if what will happen, the R value is very small or R is negligible. So we can write 1 by root of LC, which is our basic equation of the resonant frequency. So what is the current in that case? The current VR is equal to Z, and we are getting V is equal to L by CR. L by CR is also known as the equivalent or dynamic impedance of the resonance. Why it is calling the dynamic impedance? The cause of that C and L value depends on the frequency, which is dynamically changing, as the L and C value depends on the frequency, and for an AC circuit is changing, so it is called a dynamic impedance or equivalent impedance. Next, we will discuss one simple problem from this chapter. A capacitor is connected in parallel with a coil L 5.52 millihenry and resistance is equal to 10 ohm. 200 volt 50 hertz supply. So again we have to know the capacitor is connected in parallel with a coil. So coil means a practical coil whose L 5.52 and R 10 ohm. So if we want to draw it, R 10 ohm and the value of the inductor L is equal to 5.52 millihenry, and it is connected with a capacitor, and the capacitor value is given as, okay, we have to calculate the value of the capacitor, that the current taken from the supply voltage. What is the value of the supply voltage? The supply voltage is given as 100 volt 50 hertz. This is the supply voltage, 100 volt and 50 hertz. So what is happening here? First we know that Z square is equal to L by C. Z square is equal to L by C. We have just got it. What is C? C is equal to, this is, we have to calculate the capacitance. C is equal to L by Z square. Now we have to calculate the Z square value. We know that R and L, in the previous we have drawn already, that R and L is in series. So what is Z? Z is equal to square root of R square plus XL square. So what is the meaning of XL? XL is nothing but the, what is XL? XL is equal to 2 pi F into L. 2 pi F 50, this is 5.52 millihenry. So we are getting 1.734 ohm. So what is the Z square? Z square is R square we got already 10 square plus 1.734 square. So what is C? L by Z, and it is coming as 54.6 microfarad. Next, we will discuss the variation of the impedance. The variation of the impedance with the current are shown in the figure. You can see this is the variation of the current. Already we have discussed one for a normal RLC circuit. This is for an special case, that is the RL is in series and the capacitor is in parallel. So at resonance, the impedance is maximum and equals to L by CR. So this is the maximum impedance, and what is the maximum impedance value? L by CR. Consequently, what will be the current? V by Z. V by Z is equal to V by L by CR. At offset frequencies, impedance decreases. In the both side, impedance decreases. As a result, we can show. And this side, we can change the inductance is increasing from 0 to here. Inductance is in the increasing side. So L is equal to 2 pi FL. So what will happen if the frequency is increasing? The inductive value is increased. So this side is an inductive circuit. This side is an inductive circuit. And 1 by 2 pi FC. If the frequency is again increasing, or here rather we can tell we are going in this side. So frequency is decreasing means XC will increase. XC will increase means this side we can consider as the capacitive circuit. Next is what about the current? Current at resonance is minimum, we know. Hence, such a circuit which is used in the practical is known as the rejector circuits, because it rejects the frequency to which is resonance. As this type of circuit, the current is minimum, so we can think that the circuit is not working properly. So this circuit is basically known as the rejector circuit. The resonance is often referred to as the current resonance because current circulating between two branches is many times greater than the line current taken from the supply. As this is a special case, the resonant circuit, the circuit is in the RL and C branch is increasing, taking more current, and it is causing some more current in the branch. So that's why it is called the current resonance. This RLC circuit is often known as the current resonance. Sometimes the resonance in the RLC series circuit is known as the voltage resonance. So for my today's topic, I have discussed A. Chakraborty's Electrical Circuits book, the Circuits and Network books of A. Sudhakar, and Network Analysis, the basic books of Valkenburg, and the Internet. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.